In this lecture, we are going to talk about fundamental solutions, right? Now, before we move on, we are going to talk about Laplace equation in this video. Laplace equation. So this is our continuation video on Laplace equation, and essentially, let us just clear it up what we exactly want to achieve here. So essentially, we are going to talk about this is what we need to understand the well-posedness of the Dirichlet problem. Dirichlet problem given by, I will explain why I call it a Dirichlet problem, given by minus Laplacian of u equals to f in omega. As usual, omega is an open subset of Rn, and u restricted to the boundary of omega is g. Okay, this is the problem. So as you can understand, this is a Poisson problem, right? It's a Poisson equation because Laplacian of u equals to 0 is called the Poisson equation, if you remember. Okay, this is after a mathematician by the name of Poisson and a French mathematician. And if f equals to 0, that's a Laplace equation. If you have an arbitrary f, that's a Poisson equation. And u, when you restrict u to the boundary of omega, that is going to be some function g. Now here f and g are given smooth functions. Okay, given smooth functions. I mean, here I am not exactly specifying what sort of functions are there, but let's just assume there are smooth functions. Okay, so why it is called Dirichlet? Let's understand this thing. See, let's say you are given a Poisson equation, right? Minus Laplacian of u equals to f. Yeah, with this you can specify different type of boundary conditions. Yeah, so first of all, let us look at the equation and the boundary conditions. So different boundary conditions. Different boundary conditions. Let us assume that you are given a Poisson equation which looks like this: Laplacian of u equals to f. Okay, let's call that 1. So 1 plus this boundary condition that u restrict to the boundary is g. G is some function. So essentially you are given the information on u in the domain. So Laplacian of u, you know that it is equals to f in omega, and the boundary, on the boundary, the unknown function u will look like g. Yeah, if this sort of boundary condition is given, we call it a Dirichlet boundary condition. Dirichlet boundary. Clear? Dirichlet boundary. Now let's say that 1 is given plus this sort of boundary condition is given, del u del gamma at the boundary. Okay, that is equals to g, let's say. Okay, where gamma is the unit outward normal. Outward normal. Okay, to del omega. Okay, if that is the case, then this sort of boundary condition is called the Neumann condition. Okay, and this is called a, how do I put it? So that this is called a Neumann condition. Neumann boundary. Okay, there are other boundary conditions also. Let me give you another example. So let's say that's 0, 1, that's 0, 2, and 3. There are other boundary conditions you can just specify, but for now we'll just give another condition. So 1 plus, okay, so obviously this equation is there, equation plus a boundary condition. Okay, the boundary conditions look like this, something like let's say u plus del u del gamma. Okay, so this whole thing restricted to del omega, let's say that is equals to g. Okay, so you have this equation and you have this boundary condition u plus del u del gamma restricted to the boundary is g. Yeah, this sort of boundary condition is called a mixed boundary condition. mixed boundary condition. Okay. Now there are other conditions also. So let's say in some part of the boundary, let's say let's say this is your omega. Okay, that's your omega. Let's say this is your omega and that's your boundary, right? Now it may happen that in this part of the boundary, let's put it in red color. Yeah, it may happen that you are given a boundary condition like in this part of the boundary it is G, and in this part of the boundary, so U is G here on the boundary, okay, and del U del eta, let's say that is some H, some function H on this part of the boundary, okay, on this part. Okay, it may happen that you are given this equation and this sort of boundary condition, yeah, and that may also happen. So there are different options, but for now we will just restrict ourselves to the Dirichlet boundary condition. Okay, so let's see what happens. So Dirichlet problem, we say it is a Dirichlet problem. Clear? Okay, how does the Dirichlet problem look like? Minus Laplacian of u equals to f in omega, okay, and u restricted it to the boundary del omega, this is going to be G. And we'll assume f is in C of omega and G is in C omega del omega. Okay, the continuous on the boundary and f is continuous on omega. So this is the only condition which I am just taking. Now the thing is this: what do we need to do here? If you remember properly, when working with this sort of problem, we said that our main motivation to study this sort of problem is the following: we need to understand that, of course, okay, here whenever we are doing, omega is assumed to be a open connected set in Rn. Clear? So that is always assumed. Now, f is continuous and G is continuous on the boundary. We want to talk about the well-posedness of the problem. Well-posedness of, let's say that's your 1 of 1. Okay, well-posedness of 1. Okay, now first of all, let us start with this thing. See, we will not directly attack this problem, okay? We'll take it part by part. So first of all, what we are going to do is we are going to assume, yeah, we are going to assume that, so well-posedness, what does well-posedness, if you remember, first thing is existence, right? Existence. So first of all, you have to find that if there is a solution or not. Number two, uniqueness. That is that if there is a solution, is it unique? And number three is the stability. Stability is, I mean, how does the solution behave? So the solution must be small when the initial data is small. So basically, let me write it as stability of initial conditions. Stability of initial condition. Let us put it this way. Okay, initial data. Okay. Now let us look at what are the problems associated to this. Okay, so let us see, most of you guys, I'm quite sure you know, let us say if I'm asking you to solve this problem, Laplacian of u equals to 0 in omega. Clear? Okay, and omega is given to be something like this, let's say in 2 dimension. Yeah, so this is just a motivation. In 2 dimension, let's say it will look like this, right? AB cross CD. Yeah, so in this thing I want to solve this equation. Yeah, so in this rectangle, let's say I don't know, maybe something like this, huh? So this is AB cross CD, this rectangle R, let's say this is omega. Yeah, this is omega. Now if I'm asking you to solve this problem, what do? You can use the separation of variable, right? And what is it? Just roughly speaking, it will look like this. So you are basically trying to find a solution u of xy, which will look like some function of x times some function of y. Okay. Now if of course you are thinking of this as a C2 function, Now, since this is a solution, you are thinking of this as a solution of this, so you can calculate uxx, uyy, and after that put it in that equation. Given the boundary condition, you can use Fourier series to find out what the solution is. Yeah? You can do that. Okay. Now, let's say from here, if I am asking you to, so this can be done, right? So this is separation of variable. Separation of variable. So as you know, in the introductory video itself, I have told that we are not going to study about separation of variable in this course, right? Because I mean that's not, to be very frank, it's not very interesting thing to do. I mean it's just a method to solve it. A very significant method, but I mean nonetheless just one method to solve this thing. Now, the thing is, let's say you want, I'm asking you to solve this problem, f, and omega is in AB cross C. Yeah, how do you solve this thing? So, if you remember your separation of variable methods, what you do is, first of all, you try to find the eigenvalues. Try to solve the eigenvalue problem. Eigenvalue problem. Laplacian of u equals to lambda u, okay, minus Laplacian of u in omega, that is the omega AB cross CD, and u restricted to the boundary del omega is g. Okay, you just try to solve this eigenvalue problem, and then I mean you can use the data from here to actually, I mean you can use the functions from here, the solutions, okay, and you can construct a solution for f. Okay, you can construct the solution for 1. So using the uh, linearly independent eigenfunctions. So once you solve this equation, let's say this is your 2. Once you solve 2, you get some eigenfunctions, right? So when you use these eigenfunctions, I'm getting the circular. Okay, so using the linearly independent eigenfunctions, okay, one can construct the solution of 1, right? You remember? Yeah. So that's the separation of variable. Now, what is the restriction with this method? See, if this method works in any given domain, then we do not have anything to do, right? I mean, there is nothing to do here. You can just use separation of variable to solve this problem, and you can look at the explicit solution. You use the explicit solution to, I mean, that's the point, right? Once you get an explicit solution, you do not have to do anything. Existence, uniqueness, stability, all of this can be easily checked. But the problem is this separation of variable. Please remember this thing, yeah? Why we were doing this thing? The main restriction of separation of variable, this method is that it works on certain type of domains. So most if you remember, you just work out one problem using separation of variable, you will understand. See, if it is not in this form, AB cross CD, not in a rectangular form, then the separation of variable won't work. You can think of, I mean, of course, in the other coordinate system, you can think of a circle also on a disk and all. You can actually solve it, but you are essentially, whenever you are doing this change of variable to radial coordinate or spherical, cylindrical coordinates, you are essentially doing something like this. So essentially, for a domain which looks like a rectangular kind of domain or like a spherical domain, that sort of domain, separation of variable works, okay. But most of the problems which we encounter, that is not a given domain like this, right? I mean, it can be any arbitrary domain. What do you do then? That's the question. Okay, so let's look at what do we do then. See, what we do is this. Now, question is well posedness for an arbitrary domain. I hope I have made it clear why we need to study this. See, again, let me recall. The point is this: using separation of variable, you can of course get an explicit solution, right? Yeah. But the problem is the domain has to be very specific, and to be very precise, the domain has to be a rectangular domain, yeah, or a circular domain, that sort of thing, a cylindrical domain. But most of the times in applications, when you talk about domains, it may not look like that, right? The question is, how do you talk about well posedness for this? So you have to find an explicit solution. Can you always find an explicit solution? The question is, can one always derive an explicit solution on an arbitrary domain? Okay, so this is the rephrased version of this. Yeah, well posedness, the rephrased version. So can you find an explicit solution for an arbitrary domain? Okay, so the answer is this. Theoretically it is possible, but practically you can't find. So practically not possible. Not possible. Okay, theoretically it is possible. We'll talk about that. We'll use Green's function to do that. Okay, so let us just explore more. So let us just say that so there are three components, right, of well posedness: existence, uniqueness, and the stability with respect to the initial data. Okay, let us start about talk about uniqueness first. Yeah, let's just get that out of the way. So consider this problem. Let's just start with Laplacian u equals to f in omega u equals to g on the boundary. Okay, we are interested we are interested in the question of uniqueness first. Question of uniqueness. Now please understand that we haven't talked about existence, because that is a difficult part, huh? First of all, let us say that we will assume that there is a solution. We want to see that if there is one solution, yeah, can we find other solutions from there for this problem? Okay, that's the question. See, if we can find, if we can solve this problem, if you take f equals to 0, then the Laplace equation is also done, right? Okay, so this is a much general problem. So the question is, assume, uh, therefore, let's just put it this way: assume one admits admits a solution u in C2 of omega bar. Clear? Let's say that one admits a solution of u in C2 of omega. Okay. Then that solution that solution is unique. Okay. So this is a theorem. I don't know how to. Let's say theorem one. Okay. So what it is essentially saying is this. See, first of all, we need to study well posedness, right? We do not know whether that problem has a solution or not. But we are talking about uniqueness first. Yeah, for in the well posedness part, three part are there. We just want to talk about uniqueness first. We are saying that if there is one solution, yeah, at least one solution. If you can just show that there is at least one solution, you can show that that solution is unique. So we are assuming that there is at least one solution. We'll show that you cannot find any other solution. That is only one solution. Okay, there is only one solution to one. So how do you find it? Let's just take look at the proof of this thing. Okay, now I hope you understand what I meant by one solution. So there is a okay, maybe before I go on doing this thing, maybe I can talk about what do I mean by solution of this thing. Yeah, it will be better that way, I think. So just a solution of one. Sorry, I just messed up the order a little bit. Solution of one. What do I mean by a solution of one? Then we can talk about this. So solution of one, as you can understand, that u which is in C2 omega bar, okay, is called a solution of one if Laplacian of u at the point x is f of x, okay, for all x in omega and u restricted to boundary. So u of x equals to g of x for x on the boundary of omega. Okay, just a simple thing. It's only that u has to be in C2 of omega bar for now. Okay, this is what we mean by a solution. So we are saying that if you can find a solution for this problem, then the solution is unique. How do I prove this thing? Yeah. So let u tilde be any other solution. Any other solution of 1. Clear? So define w to be u minus u tilde. Okay. See, initially we have one solution u. I am also assuming that u tilde is another solution of 1. Okay. And you define w equals to u minus u tilde. Yeah. So clearly w is in C2 of omega bar, right? See, u is a solution and definitely it is in C2 of omega bar, right? U tilde is also a solution. And what do I mean by a solution? A solution to this one is a C2 of omega bar function which satisfies this. So if u tilde is another solution, u tilde has to be in C2 omega bar. Yeah. So u and u tilde are both in C2 omega bar. You can see that the u minus u tilde, the difference of those two, which is defined by w, okay, which is defined by w, that is also in C2 of omega bar. And clearly w is in C2 omega and satisfies Laplacian of w equals to 0 in omega and w equals to 0 on the boundary. Do you agree with me? See, if Laplacian of w, Laplacian is a linear operator, right? So Laplacian of w is Laplacian of u minus Laplacian of u tilde. Laplacian of u is also f, Laplacian of u tilde is also f. So Laplacian of w is going to be 0. And moreover, u is g on del omega and u tilde is also g on del omega. So w is w is 0 on the 0 on the boundary, right? Okay, so see, essentially if we define it like this, w is going to solve the Dirichlet problem, w is equals to 0, but not the Poisson problem. So it is essentially a Laplace equation. Yeah, w solves the Laplace equation. Okay, now what happens when it does that? Then you take a integration by parts. Okay, again integration by parts. Use integration by parts. What does it do? See, if you multiply this with a w, yeah, multiply both sides with w. Okay, so let's say w times Laplacian of w integral over omega, that is going to be 0. Yes, because Laplacian of, I mean, let us just assume that w is not 0. Yeah, see, if w is, so let us assume that this is a problem given to us. Yeah, if we can show that w equals to 0 is the only possible solution of this, and then we are done, right? Now, because if w is 0, u is equals to u tilde and you are done, right? So there is only one solution. Now let us assume that w is not 0, so we can just multiply it by w. So w Laplacian w, that is also 0. Okay, even if it is 0 it doesn't matter, but anyways, so integral omega w Laplacian w is equals to 0. Now if you do an integration by parts here, what will it look like? Omega gradient of w square, okay, dx. This is with respect to dx. I forgot to write dx. This is equals to 0. Yeah, because there is a boundary term, but in the boundary it is 0, w is 0. So the boundary term is not there. So this is equals to 0. If you remember, yeah. So this is integration by parts. If you do not know this, please look at the first lecture. Okay, there this integration by parts is done. So this will give you, see, the gradient w square. This is a positive function, right? You are integrating a positive function. Yeah, minus you can just throw it outside. It's not a problem. No? So you are integrating a positive function over omega, and you are saying that is equals to 0. So the positive function gradient of w has to be 0, right? So what does that mean? It means the gradient of w is 0 in omega, right? This, the integral of a positive function is 0, so the function has to be 0. Yeah, the function has to be 0. Okay. Now, so if the function, sorry, yeah, so function is has to be 0. So here the function is gradient of w. So gradient of w is 0. Yeah, and it is given that w is equals to 0 on the boundary. Okay, what is w? W is a C2 omega bar function. So it is continuous till the boundary of omega, right? On the boundary it is 0, and the derivative of w is 0 on the interior omega. What does that say? It says that w has to be 0 in omega, right? So that implies w is 0 in omega. Yeah. See, if w is non-zero somewhere in omega, yeah, it's a constant. That constant has to be there up till the boundary, because gradient of w is 0 in omega. Yeah, if the gradient is 0, then the function has to be constant. If it is a constant in omega and the constant is not 0, so on the boundary it cannot take 0. Yeah, see, if w is a constant which is non-zero in the interior of the domain, that cannot be 0 on the boundary, because w is continuous function, right? So w has to be 0 on omega, in omega, and that will imply u is equivalent to u tilde in omega. Yeah, and hence there is a unique solution. So you do not have to worry about this. See, we also proved that the Laplace equation has a unique solution, right? So essentially, what it is saying is this: if you have a Poisson equation which looks like this, Laplacian equals to f in omega and e equals to g on the boundary. Of course, f and g are nice functions. If you are given something like this, then these functions admit I mean, you see, I do not know if there is a solution or not. If you just give me one solution, then I can guarantee you that that solution is a unique solution. Clear? So uniqueness is out of the way. I mean, we don't care about uniqueness anymore. Now the question is if we can find such a solution or not. Okay, and this is the place where it gets a little complicated. Okay, let me give you a characterization of solutions, and then from there we will do a little construction to find solutions. Okay, so this is a characterization of harmonic functions. Characterization, not harmonic functions. I mean, Poisson. I mean, solutions of the Poisson equation. So characterization of solutions to the Poisson equation. Okay, we want a characterization of this thing. So this is actually this characterization. This is not very important for this course, but I just want you to know how this works. But this is the basis. So essentially, let me give you a small note. This is the basis of modern PDE. Okay, if you want to do modern PDE, this is what you need to do. I mean, this is all we do actually. Okay, this is the basis of modern PDE, and is a branch, and it's a topic. I think you can say it's a um, topic called variational principle. Variational principle in calculus of variation. Calculus of variation. Okay, what I meant by this is the below thing, whatever I am doing right now, the characterization of solutions. This, this for this course, it may not be very important, but I mean, of course, we'll use this thing. But the thing is, it's not very important. But this is most important if you are looking for a modern approach to PTE. Okay, so whatever we are doing is like 100 to 200 years old. Okay, in this course, yeah. But if you want to do the modern part, this is the modern part. So just to give you the taste of that modern part, I'm just doing this part. Okay, so essentially you are given this Poisson equation. So let me write it down. Let's say Laplacian of u equals to 0 equals to f in omega. Okay, u equals to g on the boundary. Yeah, our usual problem. We are calling it 1. So this is your 1. Now I want to talk about the solution of this problem. Okay, and while talking about the solution of this problem, I will define the energy functional. Okay, so what I meant by this is I will define a new object. For now you just think of this as a new object called I of w. Okay, and that will be given by integral over omega half gradient w square minus wf, okay, dx. Maybe I can put it in a small dx. Okay, so that is I of w. Yeah, and it is not like I mean it is coming from heavens, huh? It's not like that. There is a proper scientific way of how this is coming, and that is what we are going to I mean explain now. Essentially, let me just put down where w is. Where w belongs to this set A. Okay, and how do we define this set A? It is defined as all the functions in C2 omega bar, okay, such that, so you define a A like this, yeah, you define a set A and you take W like this, such that W equals to G on the boundary. Okay, so you are looking at a C2 omega bar function such that W equals to G on the boundary, and you look at I mean you define a I which is from this set to R. Okay, so you define I, hence I is defined from this set to R. Okay, is a linear functional. Functional is just a function. We call it a functional because it is a function from a function space to R. It is taking a function and putting it into giving you back a real number. That is why it's called a functional. Okay, sorry, it's not a linear function. It's a function. Okay, we call it a energy functional. So essentially, this actually I mean encapsulates the total energy of the system. Okay, but let's not go there. Let's just talk about what is so special about this and what is the relation between one and this energy functional. Yeah, so for that we are going to talk about a theorem. We are going to prove a theorem. Yeah, so it is called a Dirichlet theorem. Dirichlet principle. Okay, what it says, Dirichlet principle, it says that assume, let u is in C2 omega bar, okay, and it solves 1 here, then I of u, which is the minimum, okay, w is in a I of w. Okay, so what it is saying is, if you have a solution, it is saying that this, see, let's say I am looking for a solution of this problem, right? Let us assume that you guys already know what the solution is. If there is a solution of this thing, that solution actually minimizes this functional. Is it clear? This functional is some object, right? If there is a solution, that solution will be in this A. Of course it is, yeah. And you see what it is saying is, if you put that u in I, so I, if you put in u in that I, in that function, then that will give you I of u, yeah. And what is I of u? That will be the minimum of all these i's. Okay, so it minimizes the any solution of one, yeah. We have seen that any solution of one, there is only one solution to this problem, right? So what it is saying is that solution actually minimizes the energy functional. This minimizes this particular stuff IW. Okay, so you can take any W from this set A, doesn't matter. That W, the value of W is always greater than equal the value of I at the point U, where U is the solution of this problem, right? There is a converse part also. Conversely, and this is very important, huh? Conversely, if U is in A, okay, and satisfies uh, let us call this thing as 2, okay, this 2, the minimum of this is I of u, satisfies 2, okay, then u solves 1, solves 1. So very important, yeah, and very, very exciting thing. What it is saying is this. Let us say that you have a function. If you have somehow a solution, so first of all, it is saying that you give me a solution. Okay. Once you give me a solution to one, once you give me a solution to this problem one, you guys already know that if there is a solution, it has to be a unique solution, right? So once you give that unique solution to me, I can say that that solution minimizes this functional iw, which is defined by this. That solution minimizes. Conversely, if you can find a minimizer to this solution, so basically it's saying that if you can find a u in a in this set, which satisfies this, it means that, see, it means that there is a function u where the minimum is attained, where I is attaining is minimum, that is u, okay. So basically it is saying that if there is a function u where I is attained, the minimum is attained, then you can say that that function solves one. Okay, so both sides are true. This is called a Dirichlet principle. So essentially, you see, if you want to solve the problem, this problem, the Poisson equation in an arbitrary domain, what you can do is you just look at the energy functional and try to minimize the energy functional. Okay, if you can, let's say, somehow manage to find a minimizer to this energy functional, then that minimizer will turn out to be a solution to this problem. Okay, so let's prove this theorem. To prove, so choose, I'll prove this part first. So we choose W in A. Okay, W in A. Then from 1 we have C. If I take everything together, Laplacian of U minus F, okay, and U minus W. W I am taking from A, and U solves this one, right? So I am taking U minus W. So this is on omega, okay? So you see, Laplacian of U equals to F in omega. So this particular thing is 0, irrespective of where W is. U and W are in C2 of omega, or in A. U and W is in A, right? Okay, so U minus W is also in A, right? So that is, sorry, U minus W is not in A. U minus W, so U minus W is not in A. Okay, please remember this thing. So basically, but it is in C2 of omega, but U minus W is in C2 of omega bar. Okay, why it is not in A? Because on the boundary this is going to be 0, right? But on A, the boundary U minus W has to be G if it is has to be in A. Okay, so it is not in A but it is in C2. So basically the integral has to be 0. Why? Because this is 0. Laplacian of U minus Laplacian of U is equal to F in omega, right? Okay, F in, you can see. So let's write it like minus Laplacian. This is just a convention, nothing else. Yeah, minus Laplacian U equals to F, U equals to G. So see what I meant by this is, so it means minus Laplacian of U minus F is 0 in omega. Yeah, so the, if you multiply it by U minus W and integrate it over omega, that is going to be 0. Okay, now we use integration by parts. Integration by parts. If we use integration by parts, what happens? It is minus Laplacian of U times U minus W minus integral over omega F U minus W equals 0. Okay, so what does that, I mean, there is a dx, in all of this there is a dx. I'm just forgetting to write it down. There's a d of x, right? Now if you use a integration by parts here, so this is not an integration by parts, we just whatever I write here, it is, I'm using integration by parts. Okay, so that will give you gradient of u dot gradient of u minus w dx minus equals to integral over omega fu minus integral over omega fw. Again I forgot to write dx. Okay, right? So I have this. Now let us just look at, okay, now what happens, see, if you are doing integration by parts, yeah, so let's just write it like this. This is minus, this is equals to 0. So if you are doing integration bypass, there is a boundary term, right? But u minus w is 0 on the boundary. That is why we just multiplied by u minus w. Okay, u minus w, that is 0 on the boundary, right? Okay, so there is a boundary term, if you remember, in integration bypass. That boundary term is not there. Okay, so now what we do is, what it implies is this. See, this implies that gradient of u square, okay, gradient of u dot gradient of u square minus integral omega u f dx, okay, this is equals to, I will take that part here. So integral gradient of u dot gradient of w, I hope it is fine, minus integral omega u w dx, right? Again, I'm always forgetting dx is there. Okay, now if this is there, see, what does that say? This says that, uh, let us do this thing a little bit. You see, this is, here I'm using this thing. You guys already know AB is less than a square by 2 plus b square by 2, right? That's just an easy algebraic inequality. So from here, what do we get? We get integral omega gradient u square dx minus integral omega u f dx. Okay, this is less than equals to half integral omega gradient u square, okay, plus half omega gradient w square minus integral omega u w dx. Yeah, how is it coming? See, integral over omega gradient u dot gradient, so integral over omega gradient u dot gradient w, okay, this is dominated by integral over omega gradient mod gradient u dot mod gradient w. Yeah, and then you use this inequality to get this, right? Okay, so once you get this, if you take this part here, it will give you half integral omega gradient u square minus integral omega u f dx. I mean, please forgive me, I'm always forgetting dx. So this is less than equals to, I mean, if you want, you don't write dx, that's not a problem. I'm always forgetting dx. So this is half integral omega gradient of w square, okay, dx minus integral omega u w dx. Okay, so if you remember, what is it? This is I of u. This is I of u, and that is less than equal I of, this is w, right? Okay, and since u is in a, yeah, u is in a, right? So therefore minimum I of u, see, w is any arbitrary, if you remember, see, w is an arbitrary point in a, right? Huh? And u is in C2 omega such that u on the boundary is G. So u is definitely in A, right? So you see, u is in A, that implies I of u is equals to the minimum of IW, W is in A. Yeah. See, it is saying that this is the infimum, but u, since u is in A, that infimum is achieved, and that is why this is the minimum. Clear? Okay, so you have seen that if there is a solution, that solution is the minimum of this energy function. Let's look at the converse part. Conversely, okay, let's say I of u is less than equal I of w, okay, and this w is in A. Clear? It is given. Yeah, it is given to you. So sorry, I should write it as a minimum of IW. I mean, I want to write this thing. Conversely, I am assuming this. I will show that user. So maybe I can, I will write it as, conversely, let's say this is given to you, minimum of W in A, I of W. Yeah. Now I want to show that you solve the equation. How do I solve it? So you fix a V in Cc infinity omega. Okay, so basically Cc infinity omega, I am not quite sure if I defined it. It is the set of all compactly compactly supported smooth functions. Okay, smooth functions in omega. Compactly supported means, what I meant by this is, so basically support of a function is a set of all those x such that, okay, f of x is not 0. Okay, the closure of this thing. If you take the closure of this thing, that set, this is called the support of, f. Yeah, this is the set. Support of f is the set where f of x is non-zero, the closure of that set. Okay, so you are basically, and if that this kind of thing is contained in omega, yeah, if you're looking at a function such that this happens, then we say that the function has a compact support, okay, in omega. So essentially, you can think of this. Let's say a function which is zero on the boundary and some non-zero part in the interior. That kind of function has a compact support. Yeah. For example, let's say that's your boundary. Let's say this is your omega. Okay, one dimension. Let's just look at one dimension, and this sort of function are you talking about? Okay, so this has a compact support. Yeah, because it is non-zero in a compact set. In this set, if you take the closure, that is a compact set, and it is zero everywhere. So basically the compact set is contained in omega, and this is a, example of a function which has a compact support. So you start with a v which has a compact support in omega, and it is smooth, c infinity. Okay, so infinitely reversible, and define I of tau to be capital I of u plus tau v. Okay, u is this minimizer, it is given to us. V is a cc infinity function. I am just taking the convex combination of those two, u plus tau v. Okay, and where is tau? Tau is in R. Clear? Now you see, I want to look at what I does. See, u plus tau v. Do you think it is in A? Of course it is in A, right? For every tau in R, of course it is. Why? Because you see, this is the point. Why we do want a compact support function? Because v is 0 on the boundary for a compact support function, right? So on the boundary, u is basically g. Okay, and since v is cc infinity, it is also c2. Yeah, so essentially this whole thing is in A, u plus tau v. So I, this function, therefore I has a minimum at tau equals to 0, right? Because I of u, at the point u, I attains a minimum. So the small I, this will attain a minimum at tau equals to 0. Because at tau equals to 0, capital I is u, right? So capital I of u, that is where the minimum is attained. So that is why small I attains its minimum at 0. So if it is attains its minimum is 0, I can talk about I prime of 0, that is equals to 0, right? Prime is with respect to tau. So I prime is d tau. Right? Okay. So of course the derivative exists, right? The derivative exists, and it is, you can of course show it is differentiable. It's not a problem. Okay. If you are not convinced, please check that the derivative exists here. Okay. So I prime 0 is 0. Now, if I prime 0 is 0, see, but what is happening if that is 0? I of tau, okay, this is equals to half integral gradient of u plus tau v square minus integral u plus tau v times f dx, right? This is what happens, and that is equals to half integral gradient u square, okay, plus tau gradient u dot gradient v. Again, I am forgetting dx all the time. Okay, so let me do it like this: omega plus tau square by 2 gradient v square, okay, minus u plus tau v f dx. Okay, so this is the case. So therefore 0 equals to I prime of tau, I prime of 0 essentially. See, I attains minimum at 0, so I prime of 0 is 0. So that will be give you just take the derivative with respect to tau. If you take that, this is going to be 0. This is remaining and this is remaining, right? So it will look like integral over omega gradient u dot gradient v, okay, dx minus integral over omega v f dx. Okay, this is equals to integral over omega minus Laplacian of u minus f dx, right? Please understand, I of tau will look like this, right? So if you take the derivative, that derivative with respect to tau, that will go inside the integral, because this integral is with respect to x. Yeah, it has nothing to do with tau, so I can take the derivative inside. If I am taking the derivative, this term is not there. This term is only, I mean, the derivative of this term with respect to tau is only gradient u dot gradient v, which is this, and here it is tau times this one, and tau at the point 0, this term won't be there. Okay, so the only term which will be there is minus vf, which is the derivative of this term is vf, so minus vf, right? So this now you see, this holds this identity. Okay, so let's say that is 3. So 3 holds for all v in cc infinity omega, right? If this holds for all v in cc infinity omega, that will imply Laplacian of u equals to f in omega. Okay, because see, if this holds for c, so this is a small exercise if you want a exercise. So let's say u is in c2 of omega bar be such that u times phi, this is dx, is 0 over omega for all phi in cc infinity omega. That will imply u has to be 0 in omega. Okay, that's a small example. So it is basically saying that if you have a C2 function such that integral over omega u phi dx is 0 for all cc infinity functions, then it means that u is 0 in omega. So please do this thing. This I will put it in an assignment. Okay. So if this is true, then that will imply that Laplacian u equals to f, and hence you see u is in alpha, so u is g on the boundary. It is always given, and we have also showed that Laplacian u equals to f in the omega, and hence u solves the. Therefore, u solves 1. Okay. So what we proved is, if you want to solve 1, this equation, if you want to solve the 1, then if you have to find a minimizer of this functional and vice versa. Okay. With this, we are going to end this lecture.